So Brant, how did you get into astronomy? What was your path?
It was pretty accidental, actually. I wanted to be a writer, and so I went to college.
What kind of Great American Novel? Pot Boilers?
I wanted to be a poet.
Wow. Okay.
Yeah, no, it's almost embarrassing to say, but so I wanted to go to college. My brothers were of similar age, and so for my family to afford to send me to school, I had to get a scholarship. And I couldn't get one to be a poet, but I could get a scholarship to do physics and astronomy. So that's what I thought I was going to do. I was going to fool the world, be an astronomer during the day, and then actually be a writer. But it became more interesting to me than I thought it was going to be. So I just stuck with it.
So the day job took over.
That's right.
You didn't have to have a night job.
No. And I'm a theorist, so I only work during the day anyway, practically. Right. So
well, I don't know. As far as making a living, poetry, I think you probably made a good choice.
Yeah, probably. Yeah, I mean there are other paths to riches, but astronomy is a lot of fun. So so I went to the University of Washington in Seattle for my undergrad, and then I went to Harvard for grad school, and I've been at the University of Chicago and Caltech, and then now I'm here at Arizona as an assistant professor.
So maybe talk a little in general about the techniques of cosmology, because people sort of think we have model of the universe. They understand we have big telescopes and we're trying to measure microwave background and the first light and things like that. But there's also theory and simulation are a little coupled.
Right.
Methodologies that are very powerful now.
Yeah, well, at its core, almost everything is based on general relativity, a very large-scale analytical model of the expansion and evolution of the universe. But gravity is very complicated. So once you get down to smaller scales, where individual objects are affecting one another, calculating the evolution of many particles is very difficult to do analytically. So what people do is they use computers to simulate the evolution of both large and small scale structures in the universe. And so starting from our models of the initial density fluctuations early on in the universe, we can set up some initial conditions that reflect the very small density perturbations in the early universe, and allow those density perturbations that are realized by particles to grow through self-gravity. And that actually gives rise to structure in simulations that we can measure the statistical properties of and then compare with observations. And what we found is that the statistical properties of the structures reproduced in simulations match very well what we see observationally. So we think we have kind of as a baseline, in terms of the large-scale structure of the universe, a good physical model for the way that those structures form.
And people are familiar with the renaissance of building big telescopes in the last couple of decades, but you give a sense of how dramatic the transformation in our computational ability has been. Well,
it's been faster than Moore's law. So Moore's law is this idea that processors double in speed roughly once every 18 months. And certainly we've tracked along with that in terms of the scale of the simulations that we've been able to do. But there have been algorithmic advances which have actually been almost as important, if not more important, than just the pure power of the computers. And so as people become smarter and think of new ways of doing the calculations that make them faster, we can do bigger and better simulations. And so now we can simulate at fairly low resolution an appreciable volume of the universe. And at high resolution, we can simulate things like the local environment of the Milky Way.
So you're trading off your volume and your number of particles and so on. And what are the limits on number of particles? And
oh, sure, yeah. The largest simulations of large-scale structure in the universe now are close to 100 billion particles. Right. That's kind of what people are doing. People are hoping to do 1 trillion particle simulations. Those simulations can't track small-scale structure, and the reason is that the typical timescales in small-scale structure is much shorter than for larger scales. And so in order to complete the simulation in a reasonable amount of time, you have to kind of ignore the small-scale structure and just look at the large-scale evolution of the universe. If you want to model individual galaxies in a lot of detail, that can be as computationally challenging as doing a large scale. but you can't simulate the entire history of the universe typically.
Mm-hmm.
So you have to trade off time, resolution, and numbers of particles as well.
And since naively, you up the number of particles by 10 and you've got to calculate the forces between each of them, that's an ugly problem. There's a lot of good tricks to...
That's right, yeah, so I can tell you about those. So if you think about the fundamental way that gravity works, most people are taught to calculate the 1 over r squared force between individual objects. But you can see that if you have some number n of particles, to calculate the gravitational force of one particle on every other particle and repeat that for every particle in your simulation, that's an n squared calculation. So to do 1 trillion particles, you would need to do 10 to the 24 operations, and that's not possible to do.
Right.
So what people do is they use tricks. Either they use what are called Fourier transforms to measure the large-scale gravitational potential, or they use trees, computer science trees, where you kind of subdivide the particles into memory structures called trees. You can use the properties of those trees to calculate what's called a multiple expansion of the gravitational force. Both of those techniques reduce the computational cost of doing the gravitational force from this n squared to something that's much cheaper, typically n log n. And so that scales much better. It scales almost linearly with the number of particles with a logarithmic correction. And so you can do things much, much faster than you would otherwise be able to do if you did the direct summation of the gravitational force.
And what about the hardware? People visualize huge supercomputers taking up a whole building, but the hardware has evolved too.
Yeah, that's true. So we certainly make use of computers that take up entire buildings, and so it's a really exciting time because the nation, the NSF and NASA are building extremely large supercomputers, but they're actually being built off of new technologies. So one of those new technologies that people are familiar with in their everyday lives, certainly I've played video games once in a while, graphics cards that people use in their computers now can be programmed to do very, very fast calculations. They do vector calculations just like old Cray supercomputers do. Usually on your computer this is for rendering polygons on some video game.
Right.
But you can actually use this to calculate, say, the gravitational force between particles or hydrodynamical forces in gas. And so we're actually building a new supercomputer here at the University of Arizona that will be based almost entirely its computational power on these individual cards. And so one of these cards can be as powerful as, a good portion of a supercomputer. You do have to program them differently and use special algorithms, so they're not completely general purpose. But for things like astrophysical simulation, they're extremely useful. And so, that should be up and running by the fall. So that's very exciting.
And people, I'm sure some people have heard this phrase Beowulf cluster.
Yeah.
It sounds like some medieval...
Yeah, it is kind of medieval, actually. So I spent a good time of my first 2 years of graduate school building one of these things. I wired it myself. And so what a Beowulf cluster is it's just the collection of individual computers that are wired together through a network. And then you can use a special library. Typically people use a library called MPI, Message Passing Interface. And what this does is it allows you to communicate between one computer and another. And you can use them jointly as a larger computer where each individual processor is doing something in parallel, splitting up the gravitational force calculations amongst many different commodity hardware processors. And so it is a technique actually that even the supercomputers you see at national facilities nowadays are basically just giant Beowulfs with very fast networking and very high performance individual components.
Right. Now, in the commercial sector, people wonder, whether these rapid exponential gains can continue to be delivered. What is it in astrophysics? Is there an end in sight, or what's the prognosis?
Well, it's funny. So the last 2 days I spent at the High Performance Computing User Forum, which is a yearly national meeting where people like myself, astrophysicists, physicists, people from the national labs meet with the actual manufacturers of these supercomputers. And the end in sight is the exascale. Exascale is 10 to the 18, I guess.
Yeah,
Is that
right?
right? We use these code words and don't even know what
10
they
to
mean.
the 18 operations, or what's the
That's
unit?
right,
Unit?
operations per second.
Per second,
That's
okay.
right. So typical supercomputing facilities, the fastest supercomputers we have today are petaflops, 10 to the 15 per second scale kind of calculations. But to run an exaflop computer, the amount of power you would need with commodity hardware is like a nuclear reactor just for a single computer. And so really where we're going to have to go is to use lower power hardware like GPUs that while individually the individual processors on a GPU aren't themselves as powerful as say a CPU, you can get many of them and so do a massively parallel calculation and still reach the same performance. And so this requires people to change their algorithms though, and so that's what people are doing now. So a lot of the talk at these kind of high performance computing networking meetings is to figure out, how can we change the algorithms? What algorithms can we use to reach this exascale that people are pushing towards, but do so in a way that doesn't require our own power generators to do that. Yeah.
So astrophysicists like you obviously are power users of these big computers. Who are you competing for time? What are the other power users? Climate modelers,
bomb makers, which many astrophysicists model supernova explosions, which are not all that different in a lot of ways, and some people in national facilities do both in their spare time. But many of the power users that the vendors of these high performance computers are interested in are oil and gas. So seismic modeling, trying to figure out where oil deposits are, and then high frequency trading, of course, is also a big user.
Wow. What about biology? Are the biologists getting in on the game?
They do, but their techniques tend to be kind of massively serial calculations. So instead of doing needing the entire performance of a single supercomputer, they run many parallel serial jobs on individual CPUs, and so that's actually much easier to scale up than the kind of calculations that people are doing on national facility supercomputers. There are things like protein folding, which involves some very detailed physical chemistry and quantum mechanics. And that those kinds of calculations are done on supercomputers.
Right.
Yeah.
And making connection to your history, I recall, because I was on sabbatical at UW, and I remember, I think George Lake, didn't he get poached by Leroy Hood, who was doing a genomics thing?
That's right. Leroy Hood won the Nobel Prize for sequencing, I believe, DNA sequencing, and so he started a biology institute where they were doing supercomputing. George Lake is a well-known numericist and computational astrophysicist. And
I think they poached a few, if you don't do your poetry sideline, you could do your biology sideline.
Well, there's a lot of applications. So what's interesting about astrophysics is that the kind of algorithms that we use to speed up our calculations are actually widely used in other realms. And so, for those of you listening who are thinking about doing astronomy today, in the future you may decide to do something else, and your skills are transferable if you concentrate on how the computational techniques work. Astrophysics is a really fun application of those techniques, and so that's what I'll be doing. But other people, have different life choices that they'll make and go on to do other things. Yeah.
And just at the level of how that part of the discipline work, it sounds like it's an area where there's sort of like no textbook. I mean, you learn these tools as you go along, you invent your own tools, there's a small community that you communicate with, but this is not like easy to teach necessarily.
No, and because the hardware is changing so quickly, the books that teach you how to actually program this new hardware change every year, basically. And so many astronomers are completely self-taught when it comes to computer science, which is not optimal. So I learned how to code just because someone gave me a summer job to do research, and they said, figure it out. And that's progressed, and I've had to keep on top of these new changes. What we would like to see.
And that's propagating that's still pretty much how our grads learn, right?
I think that's true, and I think that's going to have to change in order to make use of the largest facilities that will be out there, because they will be using specialized hardware. That seems to be the trend, and it's difficult to make full use of that without some formal training. But luckily those kinds of skills really are very transferable, and so so that may not be a bad thing. But it is changing the way that astronomy is practically done, at least in computational astrophysics.
Right. So let's get back to the simulations and then to the science. Another level of detail and expertise in this area is how to put all of the astrophysics into the simulation. So you're talking about little particles, but doing dark matter and baryons and the gas they're not equally easy, or there are other methods involved there.
That's absolutely right.
So what are the challenges in putting a full simulation together?
Well, the problem with astrophysics is that it's multi-scale, multi-physics. So we know that there's cosmological scales. These are the scales much, much larger than galaxies or even clusters of galaxies. There's kind of galaxy cluster or group scales, so tens to hundreds of galaxies that cluster together. There's the properties and formation of individual galaxies like the Milky Way. The Milky Way is a quite complicated system on its own. It has a dark matter halo, it has a gaseous disk, it has star formation. Stars explode as supernova. There's cooling in the gas that you have to account for. There's different phases of the gas that you have to account for. They have supermassive black holes, so you have to understand the way that gas accretes onto black holes. But we can't resolve all of these scales at the same time. So typically what you run into is what's called a subgrid model. You have to somehow treat physics on the scales that you cannot resolve that are important for the scales that you do resolve. And how you do this is usually where the bodies are buried in computational astrophysics. And so one of the most important things that I'm trying to do is come up with a general way of doing this that you actually use the properties, say, of supersonically turbulent gas, which is typically what gas in galaxies are, to understand what's going on the scales below your simulation resolution limits. And so there, but that's just one thing that people do. People try a variety of different techniques to account for this. And the way
another interesting example of this talking about the multiscale, you have your cosmic scale down to galaxy scale, and now we know that what happens near supermassive black holes has an effect on out on the larger scale. So that astrophysics is many orders of magnitude smaller, even than the full galaxy scale.
That's absolutely right, and the evolution and formation of supermassive black holes. In order to understand that, you have to understand the mergers of black holes too, and that's a huge supercomputing task on its own, just to model the fully general relativistic space-time of two merging supermassive black holes. And so, typically what people do is they talk to one another. People in different fields exchange information about what's going on in the physics of the simulations that they're working on, whether it's merging black holes or galaxy formation on the scale of the Milky Way or cosmological simulations. And they try to account for the physics that are important, that actually communicate between these different scales and represent those physics in some way mathematically in the codes that they use. So that's interesting too, because you have to know a lot. You have to kind of be a jack of all trades, because there's a huge number of physical processes that you have to understand in order to model a complicated system like a galaxy.
And that leads to an interesting, almost epistemological question, which is, how much do you trust the simulation? I mean, how much do you let them guide your physical intuition? Or
I think this is an excellent issue, because I think because of the interest in astronomy, there are many people now who will take a simulation code and just simply run it and then analyze the results, but they don't really understand the content of the simulations. And even for experts who have written the codes, understand the algorithms that are used to solve the fluid dynamical equations or the gravitational force calculations, there's disagreements about what is real, robust physical results from simulations. And this is something that leads to a lot of arguments in the literature. But the truth is that these methods are approximate. For instance, fluid dynamics is an extremely complicated kind of physical system. The types of equations that you're solving are fully vector differential equations, differential equations. And so the way in which you discretize and model those, say, on a grid, you're not actually solving the analytical equation you think you're solving some approximate equation. And so understanding where those approximations actually affect the physical results is not easy to do, because it's quite complicated. And so people rely on resolution studies where they vary the resolution and see how robust the results are. And in some cases, in hydrodynamics, you can compare with experiment.
Right.
So there are, say, shallow water tabletop experiments that you can try to reproduce. And occasionally there are analytical results, but those are few and far between. And so you try to rely on simplifying the model as much as possible, because if you have too many epicycles, we call them, too many bells and whistles, then sometimes it's very difficult to really know what is a true result, or what is some numerical artifact that you've introduced by your approximations or even mistakes and bugs. They're very complicated codes,
right.
And so there's undoubtedly mistakes in them.
And we're in this sort of ironic situation where the painting the big picture, the large-scale structure, was done early on and is fairly robust, and the hard stuff is understanding individual galaxies and how they behave.
Yeah, I think that's absolutely the case. And then, of course, we rely on some physically important mechanisms in galaxy formation are things like supernova feedback. And we don't know how supernovas explode. And so, they're the most sophisticated, I would say, simulations that astrophysicists do are supernova explosion simulations, and we have difficulty making supernovas. But on galaxy scales, we just assume that they occur and try to account for them in some statistical way. But we really do need to push on all of these different physical fronts to understand what's going on. So right now, the emphasis really is on smaller scales and understanding what happens on the scales of star-forming clouds on galaxy scale simulations, or looking at very, very small details like exploding stars.
I'm gonna ask you to rewind that last thought, because that was loud. That was louder than the stupid bell every 15 minutes. So if you could remember, just rewind.
Oh, sure. Yeah, so, right now people are pushing on different fronts. In galaxy formation, the important things that we're interested in are physical mechanisms like supernova feedback and the efficiency of star formation on the scale of star-forming clouds in galaxies. But we also need to understand the way that supernova explode, and it's very difficult to do that. Some of the most sophisticated astrophysical simulations that people do that take hundreds of millions of hours literally on supercomputers are supernova explosion simulations, and the kind of dirty secret is that it's very difficult to actually get supernova to explode. It's something we don't fully understand right now, that mechanism. And so people have to work with one another and take physical insight from these different simulations on different scales to really get a full picture of the way that galaxies evolve.
And so you use that as an example. It's even more important in cosmology, given that our predicate of dark energy is based on the understanding of supernovae and that they behave similarly at different times in regions of space.
Yeah. So, it's interesting. It used to be that astrophysicists were funded by the NSF to study astrophysical phenomenon, but really what's happening now with these supernova explosion simulations is they're funded by the DOE. Some of this is historical in the sense that they're a lot like other explosions, but the DOE, because of dark energy, somehow falls under the DOE, the fundamental physics purview of the DOE. They're very interested in knowing whether supernova explode the same way or what the variation in the explosion of supernova are. It's actually a very serious scientific pursuit that people are thinking about very, very hard right now. So it's, it's not just about whether, how do you explode a supernova, but also the variations and the types of supernova that can explode. So, yeah.
So let's drop to the big picture for a bit, and what do you think? We're in a fairly mature era of cosmology.
Yeah.
The model's been around 50 years as people talk about precision cosmology, but there's still some pretty big questions out there. What do you think the big questions are at the moment?
Oh, well, we still want to know what the dark matter is. To me, that's very interesting. I want to know what type of particle is. It's kind of a fundamental physics question, but there's a lot of impact on galaxy scales that could arise. So what many people don't know, that they know that we have a very successful model for cosmology, but that model relies on the properties of dark matter, the detailed properties. And depending on what types of particles the dark matter might be, on very small scales, the scales of, say, dwarf satellites of the Milky Way, there can be changes in the structure of those dark matter halos that these galaxies live in. and the abundance and kind of what the radial profiles of these dark matter halos are can be affected if the dark matter particle is one type or another. And so understanding what the dark matter is actually it's a very important question that has effects on galaxy scales that we don't fully understand yet.
Are we able to reverse the logic and say these little galaxies are labs for dark matter, and so we can figure out what kind of dark matter it is?
Yeah, it's fascinating. So you can try to measure the abundance of very, very small galaxies and see compare that with cosmological simulations to see if they agree. The problem is that they're very hard to find, and so the number of these small things, even in the Milky Way halo, is extremely uncertain. But with LSST, the Large Synoptic Survey Telescope, we're expecting to find hopefully many, many more of these low-mass satellite galaxies around the Milky Way. And then we can, with a census of these low-mass things, we really could put some interesting constraints on the type of dark matter in that way. So, that's coming up in the next decade, and that'll be a very exciting thing that, University of Arizona is heavily involved in.
Okay, dark matter. What's another big question?
Well, of course, the dark energy. What is dark energy?
And that's just so hard to get a handle on.
Yeah, if it's a cosmological constant, the correction to Einstein's field equations that change the evolution of the universe, or whether GR has to be revised to take into account dark energy. If it's chameleon, some type of scalar particle that can act as dark energy. These are the kinds of questions that really they're extremely fundamental. They're some of the most important questions we have in the physical sciences right now.
And so we have a lot of phenomenological and observational handles on dark matter through all the various observations we do. What are our handles on dark energy now?
Well, so a lot of them actually come from solar system tests. It's quite interesting. So, some of the alternatives that we have to the cosmological constant have an effect on small scales, potentially. And so, just by looking at the evolution of man-made satellites like Voyager and their how they've been traveling around the sun for a long period of time, we can put some constraint, actually fairly strong constraints on some models of dark energy. Some models of dark energy predict that that galactic dynamics also will change, and so we can try to measure the velocity dispersion of clusters and the exterior of clusters and see how that compares with, like I mentioned, these chameleon dark energy models. And so that's very interesting. There are some astrophysical constraints that we can put directly on, these potential modifications to fundamental physics, and people are very excited about that.
And this is, of course, dark matter and dark energy are big conundrums for physics too, because everyone's got excited about the Higgs, which ties a bow around the standard model, but this is all beyond the standard model.
That's absolutely right, yeah. I mean, the Higgs was a phenomenal discovery. It's something that people were hoping for in some ways because, it would confirm some parts of the standard model, but in some ways they were a little bit disappointed because it's always more fun that something unexpected happens. So that, finding the Higgs was really a watershed event in the last year in physics. But there are many, many different types of models for dark matter, and one of the most interesting is this model called supersymmetry that actually the Higgs is connected with as well. And so, there are very well motivated models in supersymmetry where there are particles that would be just like the dark matter that we think exists in the universe. So if we could try to find some evidence for that dark matter, either in missing energy in these collider experiments like the LHC, or through direct detection experiments like the Cold Dark Matter Search or Xenon 100, some of these particle physics experiments, or indirect measures through annihilation. So dark matter is thought it's possible that it can self-annihilate and produce gamma-ray radiation. And so if you see line signatures of gamma-ray radiation at the centers of halos, dark matter halos in galaxies, that could be a signal of dark matter. And there's also the byproducts of dark matter annihilation, like positrons. And so there are experiments like AMS on the space station looking for the potential byproducts of dark matter annihilation in the local universe. So there's there's a lot of really interesting avenues in astrophysics that can bear directly on these fundamental physics questions.
Right. And now, and dark matter's been on the table for 40 or more years. Do you really feel like the next decade could be decisive in terms of all these experiments? And
I do, and the partial reason for that is there are a lot of interesting hints out there. So there's quite a bit of disagreement in the particle physics community with direct detection experiments. Some people have said that they might see evidence for light dark matter particles in Cogent and some of these other experiments, whereas CDMS and Xenon 100 say no, that's not the case. And so there's kind of interesting tension in a lot of these experiments. And whenever there's tension, that means something interesting is probably about to happen. So with these bigger and better experiments on the horizon, it seems like there's a lot of interesting science to be done. But also things like neutrino physics have been interesting in the last 5 years. They'll probably continue to progress. There's a lot of interesting physics there as well. So, and those are all astrophysical messenger. Dark matter and neutrinos are interesting for astrophysics. So we definitely have our ear to the ground, listening to see what happens.
Now, one of the things I know you're interested in is the earliest phases of galaxy formation and evolution, and people hear about first light, and why are people excited about how and when and what the first galaxies form? Why is that important to figure out?
Well, they're the initial conditions for what happens later. So the earliest forming galaxies, we don't really understand the way that galaxies like the Milky Way form. This is kind of extreme galaxy formation. It's galaxies that are forming in the first few 100 million years after the Big Bang. So how did they get there? What sets their properties? How many of them are there? And what effect do they have on the larger scale universe? The gas in the universe after recombination, after the Big Bang, radiation from the Big Bang was released, most of it was neutral. Most of intergalactic gas was neutral. But today it's almost completely ionized. And so there's a process called reionization where the neutral gas in the universe is ionized to form ionized hydrogen. And we don't know exactly when that happened, but it probably happened about the same time that the first galaxies were growing in abundance. Maybe not the very first systems, but kind of the second generation, perhaps, of galaxies. And so in 2009, there was this new camera installed on the Hubble Space Telescope called the Wide Field Camera 3, which is an infrared camera that's extremely sensitive. And using that, we've been able, I've been involved in this, been able to look back as far back as we've ever been able to see with HST. So just in the last year, we discovered galaxies at above redshift 8.5 to potentially out to redshift of 12. So that's only in the first 500 million years of universal history. And with James Webb Space Telescope, which people here at the University of Arizona are actually building some of the cameras for, we'll be able to probe even further back into close to the first 200 or 100 million years of universal history. And that'll be extremely exciting because that's kind of really the epoch where the first stars and galaxies will be forming. And so being able to find the first hints of that is very exciting with HST, but then looking forward to the next decade with James Webb Space Telescope, where we'll be able to characterize the properties of these high redshift galaxies, is just really an exciting time to be thinking about early galaxy formation.
What about the role of black holes? Now that we know every galaxy has a black hole, when and how did they form? How did they fit into the picture?
It's such an extremely interesting question, because if Xiaohui Fan here, a professor at the University of Arizona, is well known for finding these very distant quasars in the first billion years of universal history, and these quasars are powered by supermassive black holes that are 1 billion solar masses or something. And if you just simply say, well, black holes kind of have a throttle that they get regulated at in their growth. They can only grow so fast owing to some fundamental physics reasons. And so if you just say, well, let them grow as fast as they possibly can, could they have grown to be 1 billion solar masses by the time we see them in the first billion years of the universe? And the answer is almost, barely, yes, they can barely do it. But they have to be running at full speed the entire time from early in the universe. And so we really don't know how these supermassive black holes form. It's been an outstanding question for like 30 years in the literature. And so, we think that black holes grow in two ways. We think that they grow through accreting gas around them, and we think that they can grow through mergers of black holes. Mergers of black holes take a really long time to happen. So we think that early in the universe, the most important way that black holes probably grew with time was through gas accretion. There's a lot of gas around in the early universe. But you have to get the gas down to extremely small scales, sub-parsec scales around black holes to get them to grow. And so you have to constantly be driving gas down to small scales. Why is that a problem? Well, gas will retain angular momentum. So if you think about the way that the Milky Way disk forms, it's a spinning disk. That means it has a lot of angular momentum. We think that early galaxies were smaller, so there was slightly less angular momentum, but you still have to get rid of that angular momentum to allow the gas to get down to very small scales. And so one way of doing that is through mergers of galaxies. We think that mergers of galaxies happens more rapidly early in the universe, but we're not sure that they happen rapidly enough to keep the throttle on these black holes right where it needs to be to make supermassive black holes in the first billion years of the universe.
And how much of that complicated suite of astrophysical processes it can be simulated reasonably?
Well, we definitely try. So we've definitely simulated the formation of early quasars using mergers between individual galaxies. And we've demonstrated that it's possible, but these simulations assume a lot because they can't resolve the scales of the individual accretion disks around black holes. There's no way you can get to those scales in these galaxy scale simulations. And so we have to assume that basically once the gas gets down to the resolution limit of the simulation, it just falls right onto the black hole. It's not at all clear that that's an easy process. We want to understand this in more detail. So going into the next decade, this is something people are very interested in doing, trying to improve the resolution of the simulations and see how gas actually finds its way to the centers of these galaxies and onto the supermassive black holes.
And going maybe even further back, you're talking about this interesting phase of early mergers and growth of black holes and so on, but how sensitive is what happens in that phase to the seeds,
that's
the
a
first
great
generation
question.
of stars and what they leave behind?
So it definitely matters because, a black hole can roughly double its mass every 45,000 years, I think it is.
It's a good number for people to remember. To trot out at cocktail parties.
Gosh, is that the right number?
Well, that's fine.
We'll find it. We'll find it. You can find it. So anyway, so they can only roughly double their mass every so often, and so every single factor of 2 that you get early on actually matters.
Right.
And so it's thought that the earliest forming stars in the early universe, we didn't quite know how they form. And part of the problem is that when you're forming a star, you have to get rid of a lot of energy. And usually that energy is radiated away. In the local universe, there are a lot of metals, oxygen and iron. Oxygen and iron have very efficient radiative lines that can get rid of a lot of energy, but early in the universe, before the stars formed the oxygen and iron,
You got none of that.
And so you have to find other cooling mechanisms to allow stars to form. And one of the easiest ways, the only way that we know how to do it, is through forming molecular hydrogen. If you form molecular hydrogen is a coolant, but it's not a very efficient coolant. And so what happens is we think the first forming stars are quite massive. At least that was what was thought 10 years ago. And they would leave behind black holes, and those black holes would, say, be 100 or 150 solar masses. And that's a good head start. That helps quite a bit. But now as simulations have improved, people have found that as these first stars are forming, they actually can fragment and form binaries or multiple systems, and so they no longer leave behind such a large black hole. So now we've kind of one step forward, 2 steps back. We don't know what the mass spectrum of the initial black hole seeds from the first stars are, and it matters a lot for how easy it is to form a supermassive black hole by redshift 6, the first billion years of the universe.
Now you've hinted at how hard it is to find galaxies at redshift 8 or 10. If we're trying to get an observational handle on first generation of stars, is that even possible?
Well, in principle it is possible, but practically it'll be very, very difficult to do. So it turns out that even though these first stars might be very massive, the way that luminosity scales with mass in stars at the massive end doesn't help you enough to make them extremely bright. Okay, so they are very bright, but they're only as bright as, say, a globular cluster is today or something. And so they're on the galactic scale, they're relatively dim individually, It would be possible to detect them in terms of sensitivity with JWST, but we don't know where to look. And it's very difficult to do surveys with JWST because of the way that the telescope is going to be made. It's very slow at slewing, and so mapping out large areas of the sky is going to be quite difficult to do. So there's some hope that there are tricks that you could use, like gravitational lensing or some other tricks, to try to find these early first-forming stars.
Or gamma-ray bursts.
Or gamma-ray bursts. That's an excellent point. So that is an extremely confusing... So it turns out that as you go back in time and you look at the rate at which galaxies form stars, the rate at which galaxies form stars is declining rapidly as you go back in time. But what's interesting is that the rate of gamma-ray bursts is really high in the early universe. And we know that gamma-ray bursts form from...
observed or predicted?
That's observed.
Okay.
And so actually trying to understand it theoretically is a very difficult problem to do right now, because we think that gamma-ray bursts are formed in very massive stars. Massive stars are very short-lived, and so the rate at which massive stars form should track basically the star formation rate. That's going down as you get to high redshift, but the abundance of gamma-ray bursts is not going down nearly as quickly. And so we don't really know what's leading to this high rate of gamma-ray bursts in the early universe. And that may be very well connected with the way that massive stars form in the early universe. We don't know. And so yeah, that's an extra clue.
Is it a hint that with good enough instrumentation we could have gamma-ray bursts back to redshift 10, 15, 20?
Yeah, well, there are claims out to redshift of 8 already and 9. So, gamma-ray bursts are easy to find because, well, a star, even if it's massive, individual stars are hard to find. Gamma-ray bursts are extremely bright. And because we have satellites that detect gamma rays anywhere on the sky, if a gamma ray burst goes off, we detect the gamma rays right away. We can slew all of the telescopes to go and look very deeply at these for the actual optical signatures of the gamma rays, which are in the infrared at high redshift. Right. And that's been relatively successful at finding high redshift gamma ray bursts. And so, we're very interested to hopefully we'll have gamma ray satellites in space that can find gamma ray bursts for the foreseeable future, and continue to look into the distant past for these very massive deaths of massive stars. Yeah.
So maybe just as a last topic, talk a little, because it's been clear by illusion how multi-wavelength the cosmology is now. I mean, you talked about gamma rays, we've got traditional optical astronomy, things move into the infrared as you go back in redshift. You're talking about molecular hydrogen, which you might look at long wavelengths. You really have to piece the information together a lot of ways.
Yeah, so that's one of the most interesting things that people are doing in observational cosmology right now is, in the local universe, the way that we see neutral hydrogen in the local universe is through a 21 centimeter line that neutral hydrogen has a spin flip fine structure line that we can see in all galaxies in the nearby universe. But 21 centimeters, that's fairly low frequency. As you go to higher redshift, we know that there's a lot of neutral hydrogen out there, that makes up most of the baryons of the universe at early times. So we should be able to see this spin flip transition out to high redshift, but it gets to be extremely low frequency. And in fact, it moves into the same frequencies that television and radio, FM radio works at. And so people are working right now to solve technical challenges dealing with all of the terrestrial interference from our televisions and other communications to try to be able to see through that fog here locally back to very, very early times to look at the large-scale structures in the universe in neutral hydrogen. So that's something that people will be doing in the next decade that will be very, very interesting.
Right.
Yeah.
So the flavor's not chewed all out of the gum in cosmology by any means?
Well, not at all, especially with the Planck results kind of, disagreeing slightly with the WMAP results. People are very interested in knowing, what's at the heart of that matter. So there's still some surprises left out there to be found. Yeah.
Right. Okay.
All right,
thanks a lot, Brant.
Yeah, thank you.